All right, welcome to Lecture 17, Part C. So in Part C, we're moving on to a slightly different topic. So we've been talking about how to write out reactions, how you figure out how to balance reactions, how you figure out what you're making in a reaction. In this one, we're going to talk about something a little bit different in Part C. So let's go ahead and get started. Okay, in this part of the lecture, we're going to look at something called stoichiometry. What? Stoichiometry. All that is a big fancy word for when we look at a reaction, we're gonna try to figure out how much stuff we're making when we do a chemical reaction. So how much stuff do you make when you do a chemical reaction? So let's kind of start off with just kind of a general idea of what's going on here. And then we're going to basically, this is going to involve some calculations. Most of those calculations are really going to be like converting problems again. But before we get into some specific examples, let's just talk generally. What the heck is stoichiometry? So the idea of stoichiometry is we can figure out how much stuff we're going to make when we do a reaction. Now, the way you do that is you look at the reaction, and really you need to pay attention to the coefficients, because the coefficients tell me how much of everything is involved. So this reaction you're seeing on the screen right now, this is one that again happens in your life probably because you probably either have a gas heater in your house or a gas stove in your house, or maybe you have one at one point in your life. So CH4, that's natural gas. This is the formula for natural gas. Now, when you burn natural gas to heat up your house or cook your dinner or whatever, what's going to happen is going to react with oxygen. So it's going to react with O2, and we're going to make carbon dioxide and water. All right, so that's the reaction. We're making carbon dioxide and water. Now, the important thing for us to look at is, well, when we do this reaction, the coefficients tell me how much stuff is involved in this reaction. So again, if you don't see anything, it's a 1. So when you burn, for example, 1 molecule of natural gas, it's going to react with 2 molecules of oxygen, I should say. Those are my 2 oxygen molecules. We're going to form 1 molecule of carbon dioxide, and we're going to form 2 molecules of water. All right, so the coefficients tell me kind of the ratio of how much stuff is involved in this reaction. If I burn one of these, I get, for example, 1 carbon dioxide, and I get 2 water molecules getting created. Now, let me flip over, and we're going to kind of look at this in a little bit more detail. Let's kind of talk about it. So, as far as this goes, the ratio of how much stuff is in the reaction, so that's what the coefficients are all about. So if you were to burn some like natural gas tonight, some CH4 to heat up your house or whatever, you wouldn't really burn just 1 molecule. That wouldn't do anything. So let's think about like maybe using a little bit more. So let's say we were to burn, I don't know, let's do 100 molecules of CH4. And I wanted to know if you burned 100 of them. Again, I could ask you about anything. I could ask you about the carbon dioxide or whatever. I'm going to just, for the heck of it, ask you about the water. If we burn 100 molecules of CH4, how much water would you make? Well, the coefficients tell me for every one of these, I get double the amount of water. So if you burn 100 molecules of CH4, you're going to make 200 molecules of water, for example. All right, now let me be honest with you. You want to heat up your house tonight? Burning 100 molecules isn't going to do anything. All right, you need to burn way more than 100. So let's talk about maybe using even more. Let's say instead of burning 100 molecules of CH4, let's say you burned, I don't know, let's go with 1,000. If you burned 1,000 molecules of CH4, how many molecules of water would you make? Well, it's going to be twice as much. If you burn 1,000 of them, you're going to get 2,000 molecules of water. All right, let me tell you again, 1,000 molecules, that's not going to heat up your house. Let's do more. Let's say you burned, I don't know, let's pick a bigger number. Let's say you burned, I don't know, let's go with 3,000. If you burned 3,000 molecules of CH4, how many molecules of water would you make if you burned 3,000? Oh, let's see if you can think about that. You would make double. You would make 6,000 molecules of water. All right. You know what? Even 3,000 isn't going to do anything. Let's pick a bigger number. Let's say you were to burn, oh, this is kind of a random number, I don't know. Let's say you were to burn 6.02 times 10 to the 23 molecules. Wait a minute. That's not just a random number. What do you call 6.02 times 10 to the 23 molecules? Oh, what if you were to burn, in other words, a mole? If you were to burn a mole of this, CH4, this natural gas, and I was to ask you, how much water would you create? Well, it's still going to be double. If you burn a mole of CH4, you're going to get 2 moles of water being produced. So one way to think about these coefficients, they tell you the amounts. For every molecule we use, we get 2 molecules of water. Another way of saying that is, for every mole of this we use, we get twice as much. We get 2 moles of water. So we're going to do some examples. We're going to do them like maybe a little more formally, but that's basically what we're going to be doing. We're going to look at the coefficients, and if we know how much of one thing we have in a reaction, we can figure out how much of something else we're going to create. And for right now, when I say how much, I really mean how many moles. So however many moles, for example, of this you start with, you get twice as many moles of water. All right, so let's do a little example, and let's kind of do it a little more formally. We're going to flip over, and we'll do like it's going to be set up like a conversion problem. Let's get to that. All right, so what have we talked about so far? So far we've talked about how when you look at a reaction, the coefficients basically have to do with how much stuff is involved in the reaction. And you can kind of think of those coefficients as conversion factors. If you know how many moles of one thing you're using in a reaction, so we'll say moles of compound A, or whatever A is, and I want to figure out how many moles of something else are in the reaction, how many moles of somebody else, we'll call that B, are in the reaction. The way you go from moles of one thing to moles of another, it involves your coefficients. So you use your coefficients. So the coefficients are really conversion factors that have to do with how many moles of one thing are going to be involved compared to somebody else. So if we look at this reaction right here, nitrogen reacting with hydrogen, and then this compound over here, this is called ammonia. What the coefficients are telling me is for every 1 nitrogen, I'm going to need to use 3 moles of hydrogen, and I'm going to get 2 moles of ammonia. So the way you go from moles of one thing to moles of another, you look at your coefficients, all right? So as far as that goes, let's do a little example. And again, this is going to be more converting, really, all right? So this is going to be more converting. So let's look at an example. Okay, it says if you start with, oh, maybe I should erase a little bit of this. Get rid of these little squiggly lines. Okay, if you start with 6.85 moles of nitrogen, I might ask you, and I could really ask you about all kinds of different things. Right now, I'm going to ask you, how many moles of ammonia would you make? How many moles of this would you make? All right? So if you're going from moles of one compound to moles of another, we're going to be using our coefficients. Now, I should tell you, eventually we're going to bring in some other ideas like grams and liters and all kinds of stuff. But for right now, all we need to look at, moles of one thing to moles of something else, you're going to look at your coefficients. All right, and again, it's converting. So how do you convert? You write down the beginning number in unit. 6.85 moles of nitrogen. You write down the unit you're going to, or the number you're going to. How many moles of ammonia? We're solving for moles of ammonia. So we have our beginning number unit. That's the amount of nitrogen. We have what we're going to, ammonia. And the way you get from one compound to another, moles of one compound to moles of another, you use your coefficients. All right. So how did that work again? Well, whatever thing you have here, you got to get rid of it, right? And the way you get rid of it is you put it in the bottom of the next step. So I'm going to put moles of nitrogen on the bottom. Now, we also need a number, right? And the number is the coefficient. Oh, messed up there. The number is the coefficient from the balanced reaction. That, in other words, is your 1. For every 1 nitrogen, you are going to create, well, let's see here, how many moles of ammonia you're going to create. We're looking for ammonia, NH3. We're going to create 2 ammonias. We're going to create double the amount of ammonia. So this is kind of like what I was doing a minute ago, except now I'm setting it up as a conversion problem to help us be able to do the math a little easier, okay? So for every nitrogen, you're going to get twice as many ammonias. I'm looking at those coefficients. And whatever coefficient's with the ammonia, that goes on top, and it happens to be a 2. So what would I do mathematically to work this out? Well, I would just do 6.85 times 2 divided by 1. And when you work it out, how many moles are we going to make? Oh, I worked it out somewhere, right here. You're going to get 13.7 moles of ammonia. All right, so that's just our first example. We're going to do some more. We're going to do some more along these lines, and then actually not in this lecture, but in the next one, we'll start making it a little more complicated by bringing in things like grams and stuff. But for right now, we're just going to do moles to moles examples. That's going to be just using your coefficients. But let's see another one. Let's try another one. All right, let's move on. Okay, another example, kind of along the same lines, all right? So in fact, I'm even using the same reaction. All right, so nitrogen reacts with hydrogen to make ammonia. And again, the reactions there, and I should have already mentioned, yeah, for this to work, you have to have it balanced. So you see I already balanced it for you, right? We have a 2 right here and a 3 right here. And if you don't see nothing, it's a 1, right? So there's kind of a 1 right there. All right, so let's try another one. It says, if you want to make 84.5 moles of ammonia, so we want to make 84.5 moles of this. And I could ask you lots of questions, but the one I picked to ask is, how many moles of hydrogen would you use? How many moles of hydrogen would you need? All right, so if you want to make 84.5 moles of ammonia, NH3, how many moles of hydrogen would you use? All right, so this is converting really. The conversion factors are your coefficients. So write down your beginning number and unit. 84.5 moles of ammonia. Write down what you're going to. So what are we trying to get to? Well, how many moles of hydrogen? So we're solving for moles of hydrogen. All right. And in the middle, we're going to have to use our conversion factors. Our conversion factors are the coefficients. All right, so our beginning number is 84.5 moles of NH3. How many moles of hydrogen? All right, so let's see if this is making a little sense. All right, you have ammonia here. So that means you need to put ammonia on the bottom to get rid of it. Moles of ammonia to be exact. What number goes on the bottom? Oh, it should be ammonia's coefficient, which is a 2. Okay, yeah. So if you want to get rid of ammonia, you put it on the bottom. That makes its coefficient go on the bottom. All right. Now, we are solving for hydrogen. So we're going to put hydrogen on top. That's what we're looking for after all. And you need a number up there. What number goes up there? Oh, it should be a 3. So you need a 3 there because you put hydrogen's coefficient on the top. Now, does this look right? I hope so, right? We have ammonia here and then ammonia here. It cancels. The thing I'm left with is hydrogen, which is what I wanted. So how would you type this in your calculator? You would do 84.5 times 3 divided by 2. And if you work it out, the number I got you might have to round a little bit, but basically it should turn out to be 127. That's what I got, 127. All right, so moles of one thing to moles of another, you get there by using your coefficients. It's converting really. All right, Let's try one last one in this video. Let's try one more. Let's try one more. All right, let me flip over. Okay, for our last example, we're going to look at another reaction. So this one is actually a reaction that you might have seen in a movie. Like back a while ago, a movie called Apollo 13 came out. And that movie was based on a real story. It had Tom Hanks in it and Kevin Bacon. I think this is Bill Paxton. And they were playing some astronauts, you know, on their way to the moon. And while they're on their way to the moon, there was this accident that happened. And they had to kind of go into a smaller part of the space rocket than they were expecting to be in. When they were in there, they were looking at a gauge, and they noticed that the amount of carbon dioxide was going up. So it was going up and up and up. And that's a problem, because if there's too much carbon dioxide in a small space, you know, you could suffocate from it. So, you know, the carbon dioxide, it was building up because they were breathing. And when you exhale, the CO2 gets released from your lungs. And if you're sitting in too small a space, it can build up and actually suffocate you. So this happened in real life. And the way that you get rid of CO2 like this, that gas, is you have to make like a filtering system. So this is a picture of like the real astronauts. And they made a filtering system with some duct tape and some tubing and so on to get rid of the carbon dioxide. So in this little box here, they put this compound. And that compound, that's lithium hydroxide. So if you have carbon dioxide, that gas, and it's around lithium hydroxide, it'll react and it'll turn into stuff that's harmless. It'll turn into carbon dioxide, and the other product you'll make, it'll turn into water, I misspoke there, and it'll also turn into lithium carbonate. All right, so using this reaction, you can get rid of carbon dioxide, and that's what happened in the movie. As soon as they set up this filter system, the amount of CO2 went down, and they're like, oh, we're okay, we're gonna live. So let's do a little example of some calculations based on this reaction. So let me flip over, and let's say we're doing this reaction, and let's say in that box we had 78.2 moles of lithium hydroxide. And instead of saying make, let's say, it might be better to say use. If you want to use 78.2 moles of lithium hydroxide, I could ask you about the water or the lithium carbonate, but let me ask you about the carbon dioxide. How many moles of carbon dioxide would react away? How many moles of carbon dioxide would react away? All right, so if you've got 78.2 moles of lithium hydroxide, how many moles of CO2 are going to react away? How many moles of CO2 would be involved in this reaction? So I think, you know, instead of me doing it, I'm going to give you a shot to try this one, okay? So you gotta think about how to get lithium hydroxide to cancel out and how to end up with carbon dioxide instead. So, all right, we're going to take a little pause, and I'm going to let you work on this one. What's the answer? How many moles of CO2 would react away? All right, I hope you got that one right. If not, we're going to practice this some more. This is just the beginning of our time looking at these reactions and stoichiometry and so on. So we'll practice it in Zoom, and you'll actually even see a lot more about it in the next lecture. So that's it for this one. I hope it's making sense. If not, you can get a hold of me. I'll help you out. Zoom or email or whatever. You got my phone number. You can even call me. All right. Have a good rest of your day, and I will see you next time.